All right, let's jump right in. We are about to explore one of the most powerful and, if I'm being honest, one of the most mind-bending ideas in all of astrophysics. It's the idea that on the grandest of scales, the entire universe, well, it flows. So let me ask you a question. It kind of sounds like the start of a weird joke, right? You've got this blazing ball of nuclear fire, a swirling city of hundreds of billions of suns, and, the water coming out of your kitchen faucet. What on earth could possibly tie all of those things together? Believe it or not, that's the answer. From a certain point of view, they all behave like fluids. And this simple, really elegant concept is the key that unlocks our ability to understand the structure and the life story of some of the most massive objects we know of. So, how does that even work? Well, it's all about perspective. I mean, think about it. When you're studying an entire galaxy, you're not going to track the path of every single individual star. That's impossible. So instead, you zoom out. You look at the big picture, the collective, average behavior of all those stars moving together. And this is the more formal idea behind it. We start treating these huge collections of stars or gas particles as if they're a single continuous substance. We stop caring about the random wiggle of one little particle and instead focus on the average density or the average velocity of a whole chunk of space. That gives us a much, much clearer picture of what's actually going on. And just look at the sheer variety here. This is what makes this idea so incredibly useful. It's not some niche theory. It's like a universal toolkit for the cosmos. You can apply it to the super dense plasma burning inside stars, the unbelievably thin gas floating between galaxies, those violent jets shooting out from black holes, and even the bizarre exotic matter inside dead stars like white dwarfs and neutron stars. It works for all of them. Okay, so if you're going to treat the whole universe like a fluid, you need a basic building block to work with, right? Since scientists can't possibly track every atom, they came up with this really clever conceptual tool just to make the math manageable. And here it is, the fluid element. The best way to think about it is like the perfect sample size. It has to be big enough to have millions, maybe billions of particles inside, so you get a really stable, reliable average for things like temperature and density. But it also has to be tiny compared to the whole star or galaxy, so you can treat it as a single point in your equations. It's the perfect bridge between the messy, chaotic reality of space and the clean, elegant world of math. Now, this is a really crucial distinction to make. On the left, you've got what's called a collisional fluid. Think of the gas inside a star. All those particles are packed in so tight, they're constantly slamming into each other, and all those collisions create a very real thermal pressure. But on the right, you have a non-collisional fluid, like the stars in a galaxy. They're so incredibly far apart, they almost never actually hit each other. So in that case, it's the collective pull of gravity that shapes their flow, not particle collisions. And this all leads us to the central drama, really, of pretty much every major structure in the cosmos. It's a story that plays out inside every star, in every galaxy. It is a constant, epic battle, a cosmic tug-of-war between two fundamental forces. So in one corner, we've got pressure. This is the force pushing everything outward. It's all that thermal energy from particles zipping around and bumping into each other, constantly trying to make the star or gas cloud expand. And in the other corner, you have gravity. This is that relentless inward pull. It's generated by the object's own mass, and it's always trying to crush everything down into the smallest possible point. Now, for most of their lives, stars exist in this beautiful, delicate balance between these two forces. That outward push from pressure perfectly cancels out the inward pull of gravity. This stable state is called hydrostatic equilibrium, and it is the fundamental reason our sun is a nice, stable sphere of light and not, an exploding bomb or a collapsing black hole. So this cosmic tug-of-war isn't just a random fight. It follows a very specific set of rules. These are the basic laws of physics that tell us how any fluid, whether it's flowing in a pipe or churning inside a star, is going to behave. And even though the actual equations are super complex, the ideas behind them are beautifully simple. First, conservation of mass. Basically, stuff doesn't just appear or disappear. Second, conservation of momentum. Things keep moving the way they're moving unless something pushes them. And third, conservation of energy. You can change its form from heat to motion, but you can't create or destroy it. That's it. That's the entire rulebook. So, what's the big payoff here? We've got our concept of a fluid, we have this tug-of-war between pressure and gravity, and we have the basic rules of the game. What can we actually do with all this? Well, the payoff is huge. We can literally build a mathematical model that tells us what the inside of a star looks like, layer by layer. By applying all these principles of fluid dynamics, scientists can use a special tool called the Lane-Emden equation to calculate everything about a star, its density, its temperature, from the scorching hot core all the way out to its surface. And this right here is the incredible result of all that math. This graph is not a picture taken by a telescope. It is a direct prediction from the theory. It shows exactly how the density of a star, when you model it as a simple fluid, should be highest at the center and then smoothly drop off as you move towards the surface. This is how, without ever sending a probe, we can effectively see right into the heart of a star.
And this isn't just some abstract theory. These simplified fluid models of stars, which have the technical name polytropes, they actually produce incredibly realistic results. As this quote from a famous astrophysics paper points out, the math predicts objects with finite radii and masses. In other words, the fluid model isn't just a fun thought experiment. It actually describes something that could really physically exist out there in the universe. Which, of course, brings us to a final, really thrilling question. We've seen how this perfect balance, this equilibrium between pressure and gravity, creates stable stars that can shine for billions of years. But what happens when that balance is broken? What happens when one of those forces finally wins the cosmic tug of war? Well, that's when you get some of the most spectacular and violent events in the entire cosmos.